Okay, thank you. Okay, thanks, Giacomo. So indeed, I will start this workshop with a sort of introduction, or maybe even a lecture to classical integrability in two-dimensional field theories. So I will be quite pedagogical, I think, and probably maybe a bit boring for people that are working in this area. But so the main reason is a bit to help introduce this subject to people working more from the duality side that are interested in this conference. So let me start with giving you a sort of brief motivation of why we like integrable models. So the main reason is that if you have an integrable model, you have several methods at your display to find exact solutions of a dynamical system. Typically, it can be a quite difficult dynamical system. And so having an integrable model allows you to make some progress. So in particular, I'm thinking about Liouville's quadrature or more about more advanced methods like classical inverse scattering and so on. Now, I want to point out that an integrable model does not necessarily mean that it is solvable. So you can have an integrable model that is not solvable or the other way around. But rather the interest is having all these methods at your display. Okay, and also there are a set of numerous applications of integrable field theory. So mainly you see them occurring in fluid dynamics, condensed matter physics, and they're also used as toy models for higher dimensional strongly coupled gauge theories. But maybe for us, the main motivation would be that they also appear in string theory as an integrable field theory on the worldsheet. And this has proven to be quite useful to perform rigorous tests of the ADS-CFT correspondence. So in particular for the ADS5 cross S5 and super Yang-Mills. It was shown that there is in the planar limit, these theories are integrable, and that was used to match S matrices as well as the exact spectrum of anomalous dimensions and energies of the string. Okay, so in this lecture itself, I will be introducing integrable field theories first by introducing you finite dimensional systems, and then of course field theories, and then I will use a particular example to illustrate all the concepts that we will see. And that example is called the Principal Chiral Model. So I will be basing this hour on a set of lecture notes or books that you can consult here. So in the talk, I will often refer to the book, and with that I mean the Introduction to Classical Integrable Systems by Babylon, Bernard and Talon, so the first reference that you see here. I also advise you all these other nice lecture notes that I've written down here to take a look at. Okay, so I will start with the first part. So classical integrability for a finite dimensional system is mainly captured by Liouville's theorem. And that says that if you have a classical system with a finite number of degrees of freedom, which I denote here by n, so n is a number of canonical coordinates and momenta, and you have a Hamiltonian H that is generating time evolution tau by the Poisson brackets, then this system is called Liouville integrable if you can find n independent conserved charges, so as many conserved charges as degrees of freedom. And these conserved charges, they also need to be in involution, and that means that Poisson brackets of these conserved charges, so here, if you can see, yeah, okay, should be commutative. Right, okay. And in that case, the equations of motion can be solved by what is called quadratures. And this is really a fancy name. Oh, sorry. This is really a fancy name of really performing a finite number of integrals and algebraic equations. I will not go into that, but I advise you to take a look at the notes of Torrielli, where he really goes into the details of these methods. Now, let me point out that these, of course, these conserved charges, they will contain the Hamiltonian age, because this is a conserved charge. And also that people also speak about weak integrability if you can find these n-independent conserved charges. And then it is said that the system is strongly integrable if they are found to be in involution as well. And typical examples are the harmonic oscillator and Kepler's problem in 3 dimensions. Okay, now, so this was quite a general way of defining integrability. A more useful formulation is known as the Lax-Pair formulation. And here, this will be a formulation that I will be focusing on because it will be very straightforward to use and to generalize to two-dimensional field theories. So in this formulation, we need to assume that equations of motion can be rewritten in a particular form, namely in terms of two what we call Lax pairs, which are these matrices L and M. So the equation of motion should be able to be rewritten as the time derivative of this L matrix, and that should be giving you a commutator of the L matrix with some other matrix M. And these are so n times n phase space valued non-singular matrices. And so if you're able to write the equations of motion in this way, then it is easily find that the trace of this L matrix L and the power of it, if you take the trace, and this object would be conserved. So you need to use these equations of motion, and then you easily find indeed that they are time independent. And so this is true for every power, every integer power of this Lax matrix. And therefore, if I also assume that the eigenvalues of L are non-degenerate, then these n eigenvalues, they will be conserved charges. And so these matrices, I will be calling them Lax pairs. And let me also say that it might be quite difficult to rewrite the equations of motions in this way, but once you have these Lax pairs, then it's very easy to find these conserved charges. Okay, now to have Liouville integrability, I told you these charges also need to be in involution. So before discussing that, let me first introduce some notation that Sylvain will be using as well. Let's try to remember it up until his talk. So in general, these L and M are matrices, as I told you, so they will be in a Lie algebra. In the most general case, they would be in the general linear Lie algebra. And I will be constructing a tensor product of this Lie algebra with itself, so G cross G. And elements of this tensor product, they will be denoted by X with an index 1 underlined, and that means that this object X, which is a Lie algebra object, is taking values in the first term of a tensor product. And when I have a 2 underlined, then it takes values in the second tensor product here. Now I can also introduce sort of matrices in this space. So I have an R matrix where the 1 and the 2 is underlined. So that means that I have a matrix RAB, and then the Lie algebra generators valued in each of these terms of the tensor product. And then an object that will also appear is a Casimir operator, which is this C matrix. And then the matrix associated to it, this eta AB, can be thought of as a metric on the Lie algebra. So here I would be assuming that the algebra is semi-simple. But more importantly is that we need this notation to define the Poisson brackets in this space. So if I take a Poisson bracket of such an object, that I'm taking really the Poisson bracket of these Lie algebra elements, and then I'm valuing the Lie algebra generators in this product space. Okay, so that was just some notation. Now there's a nice proof in the book that if you can write the Poisson brackets of this Lax matrix, this L, in terms of some commutators of what is now a quite arbitrary R matrix R12, then you can show that the charges that you find from the Lax matrix will be in involution. So really this relation can be used as a sort of test to see if you have charges in involution. Okay, So within the Lax pair formulation, let me conclude the finite dimensional systems. So if you have a finite dimensional system where you can rewrite the equations of motion in terms of this Lax pair, and you can rewrite the Poisson brackets in terms of some R matrix, then the system will be classically Liouville integrable. Of course, these are just, in a strict sense, these are sufficient conditions, but they are, however, the most convenient to display the integrable structure and use several other methods rather than only Liouville's quadratures methods. And also this is the formulation that is convenient to generalize to field theories. Right, but first let me give you a few comments. So there has been in the past a lot of work in trying to classify all these consistent integrable systems where you have a Lax pair and an R matrix. So in full generality, there's no complete classification. However, there are a large number of classes of consistent R matrices. In particular, an important class is one where the R matrix is constant, so it doesn't depend on the coordinates. It is Q, and it should satisfy what is the classical Yang-Baxter equation, which is written here, such that the Poisson brackets for the Lax matrix satisfies the Jacobi identity. And a typical solution of this classical Yang-Baxter equation is a rational R matrix. Okay, then another comment is that these Lax pairs are not necessarily unique. So for us, what will be nice is that you can sort of do what we call a gauge transformation of this Lax pair with some phase space valued matrix G. And then so these Lax pairs will transform, but this will preserve the structure of the equations of motion, as well as the Poisson brackets when the R matrix transforms as well. And then the last comment is that for some classical systems, the Lax pairs can also depend on a free parameter. And then in that case, that is called a spectral parameter. And this is actually what will be useful or necessary for field theories, as we will see in a moment. Okay, so now I will go to part 2. So in the case of a field theory, you could ask, is there such a sensible thing as having Liouville integrability? And in the strict sense, no, the answer is no, because if I go from a classical system to a classical field theory, then the number of degrees of freedom becomes infinite. So it's not really well defined having Liouville integrability. However, there is a sort of natural generalization within the Lax pair formulation, and which allows you to have all these typical methods to solve your system. So here I will be focusing on two-dimensional field theories, in particular mostly in part 3, I will be focusing on sigma models. And the reason is that in higher dimensions at the quantum level, integrable field theories will be trivial. And also what is nice of having these two-dimensional models is that they apply directly to string models, if they are sigma models as well. So in the case of a sigma model, the theory would be living on, so this happened again. The theory would be living on this space-time sigma, which you can think about as being the world sheet parameterized by a time component tau and a spatial component sigma. And then the fields of these theories are maps from this space to a space with a global symmetry G, for example. Okay, good. So having integrability in such a field theory, now instead of having these Lax pairs, L and M, I will be asking that the theory has a one form on the world sheet, which is valued in the loop algebra associated to the Lie algebra. N is also depends on, has a free spectral parameter. And so this one form is what we call the Lax connection, is denoted by this curly L. And so, yeah, it's really one form on the world sheet. Now, again, we will suppose that the equations of motions can be rewritten in a sort of particular way. In this case, the lax connection will have to satisfy what is called what is a flatness condition, and the fact that we have a flatness condition for every for a free value of this spectral parameter, that will allow you to generate an infinite tower of conserved charges. Now, before showing you this, I will introduce a bit of notation and sort of objects that we will need. So first of all, this flatness condition for this lax connection can be thought of as a compatibility condition of a related auxiliary system in terms of what we call a wave function psi. So here d is the exterior derivative, and then we have plus L, which should be acting on this wave function. And the reason why it's called a wave function is because there's some similarities with nonlinear Schrödinger equations or Schrödinger equations with time-dependent potential. Now, this auxiliary system can be solved in the usual way. You probably know how to do it. So you take the path-ordered exponential of the integral of this lax connection. Now, important is that the path of the integration is, so it goes from a particular point 0, 0 to a point tau sigma. But the way you take the path is not important because this lax connection is flat. So there is a path independence because of that. Now, the second object that I want to introduce is the transport matrix, and it's a particular combination of this wave function, and you will find that you can write it as a path-ordered exponential of an integration of the spatial component of the lax pair integrated from a point A to a point B. So I will be calling this the transport matrix from A to B. Right. Okay, so now a nice and important property of this transport matrix is that if I take the time derivative of this guy, then what I find on the right-hand side will almost be like a commutator. So I find here the transport matrix from A to B, and then the time component of the lax valued on sigma is A, minus the time component of the lax valued on sigma is B, and then a transport from A to B again. And so here I really needed also this flatness condition. Now, this worldsheet or this space-time I will consider two particular cases for this space. So either I take this worldsheet to be the infinite line. In that case, you typically use asymptotically fall-off boundary conditions for your field. So here the fields are denoted by phi. And you assume the same thing for this for the components of the lax pair, so that at infinity they go to 0. So then if I would take the transport matrix from minus infinity to plus infinity, then trivially this right-hand side here will be 0. And so taking the tau derivative of this T matrix is giving you conserved charges. In particular, I can take an arbitrary number of powers of this guy, or I can Taylor expand in this free spectral parameter. Now, sort of the same is true if I take this worldsheet to be a cylinder, which would be interesting for closed strings. Then we demand periodic boundary conditions on these components of the lax pair. So, and in that case, on the right-hand side, I get a commutator because A and B will be the same. And therefore, if I take the trace of this guy and then the time derivative, I will find 0. And again, I have these conserved charges by Taylor expanding in Z or taking an arbitrary number of powers. So, and these two objects, either the transport from minus infinity to plus infinity or from 0 to 2 pi, I will be calling them the monodromy matrix. And as I told you, they generate charges. Now, I want to point out that, so I do not need to take a trace in the case of this infinite line, but nothing is stopping me from taking a trace. So I could also take a trace here if I want. Okay, so then a few remarks. I will not say something about the first two remarks in view of time, but the latter two are maybe important for the rest of the talk. So again, this lax connection will not be unique. You can perform a sort of gauge transformation a matrix that can be quite arbitrary, so it can depend on the worldsheet coordinates and also on the spectral parameter. In that case, the lax can transform in this way, and this will leave the flatness condition invariant. Now the transport matrix will also transform in that case, and it will transform in terms of conjugation by this matrix G. And then typically the charges that you find from these monodromy matrices can be sort of divided in two classes. Namely, you can have local charges, which I will discuss briefly in a minute. And you can also have non-local charges, which we will see appearing in the Principal Chiral Model. So in the example of the final part of this talk. So this is a quick, I will be quite quick about explaining these local charges, but there's a very general procedure how to get these local charges. And therefore, you really need to perform these gauge transformations. So you assume that the lax connection has a number of poles, and you perform a gauge transformation around these poles. And it turns out you can find a proof in this book that there's enough freedom in such a matrix G, depending on Z, on the spectral parameter. There's enough freedom in that matrix to really perform a gauge transformation such that the lax connection becomes diagonal. And this procedure is also called abelianization. And if the lax is diagonal, then you know that the flatness condition had this L wedge L, so sort of commutator, and so that term will vanish, and then what is left of the flatness condition will be really a conservation law. So you can find in this way conserved charges associated to this conservation law here. Now let me just say that I didn't really need the monodromy matrix, and I didn't really need to expand the monodromy matrix to find these charges, but they also appear if I do the gauge transformation on this monodromy matrix, and they appear in this way, the way that I write down here. So you see that the path ordered exponential will drop out because I have diagonalized this lax connection, and then so the charges you will find as coefficients in the sum here. Okay, so now we want to sort of mimic what happens for classical systems. So we also ask that the charges are sort of in involution, so that the Poisson brackets of your theory taken on these transport matrices, that it would give you 0. And again, you will find certain necessary relations for this lax connection to ensure that these charges are in involution. And there are particularly two interesting classes that I want to discuss. So first of all, you can have Poisson brackets, which are called ultralocal, meaning that they only have in there on the right-hand side of the Poisson bracket a Dirac delta distribution. And so what we need to do is we need to take the Poisson bracket of the spatial components of the lax here, valued at different space points, but also valued at different spectral parameter values. And so if they take this particular relation of a commutator with some matrix, again, this R matrix, then I will find that these transport matrices will satisfy this relation here. So again, a commutator with this R matrix. And these are quite important relations. They are called the Yangian exchange relations, and they are really the starting point of quantizing your theory with what is called a quantum inverse scattering method. I will not go into any detail of this, but it's nice to know. Right, and if you have these Yangian exchange relations, and because you have a commutator on the right-hand side, if I then take a trace in each of the tensor products, then I will find 0 for every power of the transport matrix, and also for every value of Z and Z prime. Now, as before, we have some sort of consistency relations on these R matrices that appear here. So, for example, if the R matrix is again constant and skew, is now skew in this particular way, and it satisfies this classical Yang-Baxter equation, then the Jacobi identity for these Poisson brackets will be satisfied. So these would be consistent R matrices. And again, typical examples are rational R matrices. Now, a second class of Poisson brackets, and this is the one that we will encounter in the Principal Chiral Model. These Poisson brackets are called non-ultralocal, and they will involve derivatives of the Dirac delta distribution. So there's also possibilities of higher derivatives, but these are not understood at all. But so if you have a particular form for these Poisson brackets of the Lax connection involving a derivative of a Dirac delta in this way, so times some matrix S, which is really sort of a symmetrization of this R matrix, and then commutators here in this way. Then we will call these Poisson brackets of Maillet RS form, and they allow some sort of progress. So let me just first point out that if this R matrix here was skew as before, then this term would actually vanish. So then this S matrix would vanish and you would not have a non-ultralocal term. So it's important that it's not skew here actually. Now, having this non-ultralocal term complicates things if you want to calculate the Poisson brackets of these transport matrices, because they involve this path-ordered exponential of an integral. So this will give you a lot of ambiguities and discontinuities, but there's some very subtle prescription to handle those, which was handled by Maillet in '86. I will not discuss this, but if you want, you can find some reviews in these papers by Dori and Vicero in 2006 and 2008. And then, so what they did is actually show that the Poisson brackets of the transport matrix, again, if you take traces, will be 0. And so in this sense, you could be sort of happy with having charges in involution, although these sort of relations are not very easy or cannot be really used to do the usual quantization in terms of the quantum inverse scattering method. So the quantization of such theories with these Poisson brackets are quite hard and not fully understood. Now, what people usually do, and it's also something that Stein will discuss, is a sort of S matrix bootstrap, where you kind of guess the S matrix using symmetries, as well as consistency relations on the S matrix, such as analyticity and unitarity. Okay, so I can conclude this part of two-dimensional integrable field theories by saying that if you have a formulation of the equations of motion in terms of a flat Lax connection that depends on a free spectral parameter Z, and the Poisson brackets are of these forms, the Sklianian exchange relations or these Maillet brackets, then we say that the system is classically integrable. Now, I want to point out that the typical classical integrable methods to then sort of solve the equations of motion and get a semi-classical solution for the spectrum. And these methods are called classical inverse scattering or classical spectral curve. They are really depending on the Lax formulation, so on the Lax pair, the transport matrix, or the wave function. And they don't necessarily need these Poisson brackets relations. So the Poisson brackets relations are quite important for the quantization of the theory rather than these classical integrable methods. And so typical examples of such theories is the Principal Chiral model that we will see, also the Sine-Gordon model or the Gros-Neveu model, etc. Are integrable field theories. Okay, so now we are ready to go to the Principal Chiral Model. So first of all, why did I choose this model to illustrate some of these concepts? So there's two main reasons why the Principal Chiral Model has an interest to study. So first of all, already since a while ago now, these models are used to study as a prototype, as a two-dimensional integrable prototype of four-dimensional Yang-Mills theory. So these models are actually asymptotically free in the UV and strongly coupled in the IR, and they dynamically generate the mass gap. And then in more the string community, they're interesting because they're sort of a building block of many string worldsheet sigma models, which have been important for ADS-CFT. So for example, if I want to study the classical integrability structure of the ADS5 cross S5, you would typically start with the Principal Chiral Model and then build up and generalize such that you can eventually understand ADS5 cross S5. So that's really the main reason. Okay, so the action, how does this model particularly looks like? So it's a sigma model, which is which is a theory on this worldsheet sigma, again parameterized by tau and sigma, and the fields of this model are maps going from this space-time to a Lie group manifold G. So you have a global symmetry manifest, and so these fields I denote by little g. And I will consider two cases. Either they will be periodic, so I will have sort of closed strings, or they are asymptotically fall off boundary conditions. And so the action I write down here, so we have in front of the integral, we have this kappa squared over 4 pi, where kappa will be the coupling. And this is actually the guy that will start running if I go to the quantum theory. And then the action is a trace of g minus 1 dg and then product with g minus 1 dg again, where this g minus 1 dg is valued in the Lie algebra associated to this Lie group G. And it's also what we call a Marusch-Cartan form. Okay, so what is nice about this theory is that it has a big global symmetry, a G left cross GR global symmetry, which acts as sending the fields G, well, it's acting on the left, either on the left with a constant group element or on the right on these fields. And the conserved currents related to this global symmetry are precisely these Marusch-Cartan forms. So the conserved current related to the left symmetry is the right invariant Marusch-Cartan form. So it's this TG G minus 1. And then the Marusch-Cartan current related to the right acting symmetry to GR will be the left invariant Marusch-Cartan form, so G minus 1 dg. Okay, good. So what is also nice is that the equations of motion of this Principal Chiral Model coincides precisely with the conservation laws of these conserved currents or these Marusch-Cartan forms. So I've written them down here in components and in terms of the fields. You can rewrite them obviously in this definition of the Marusch-Cartan form, or in a differential form language where we have D, which is the exterior derivative on the worldsheet, and then the hot star on the worldsheet of this current L equals 0. And you can show very, very easily that if this holds, then also this conservation law for the right invariant Marusch-Cartan form holds. Now, the Noether charges related to these global symmetries are simply integrals of the time components of the current. So here we have the charge related to the right. Right symmetry will be the left invariant Marusch-Cartan form, and vice versa for the other one. Now, these Marusch-Cartan forms, they satisfy by definition a Marusch-Cartan identity, and this will be quite useful because it's precisely a flatness condition. So we have the L plus L wedge L equals 0, and for the right invariant Marusch-Cartan form, we have a minus sign on the wedge. Now you could ask, can I now build like a flat lax connection that is depending on a free spectral parameter on shell? And so note that we already have a flatness condition here, but this Marusch-Cartan current L is not depending on any free parameter. So still I need a guy that also depends on a free parameter. And a smart answer that you can make to find such a lax connection is taking some linear combination of the current L and the hot star of the current. And so we have alpha and beta being the coefficients, so the arbitrary coefficients, which can be some complex numbers. So what you do is you stick this guy in the flatness conditions that you want for your lax. So you stick it in here. And you find on shells, so using the equations of motion and also this Marsh-Cartan identity, that the right-hand side is 0 when you impose a particular relation between alpha and beta. So you want that this thing here is 0. So we have indeed a 1 parameter redundancy. So I really need to impose only one relation. I don't need to specify both alpha and beta. And therefore there is some freedom in this lax in this ansatz, in this lax pair. So in particular, I should take well, a nice form is to take alpha to be of this form in terms of some parameter, some free parameter z, and beta is written instead in terms of set in this way. Then this relation will be satisfied, as you can check, and you have this free parameter z. So the lax connection in that case will look like this. And so it flattens, and in this case, and really imposes, there's a one-to-one thing with the equations of motions. Okay, so if I then have this lax pair, I can now build this monodromy matrix. Now I will focus on the infinite line here. And so I will take the monodromy matrix from -infinity to +infinity, and then you have here the spatial component of the lax appearing in this path, or the exponential. And this guy will generate then an infinite tower of conserved charges. Okay, so, oh, sorry. Yeah, so how will these charges look like? I told you you should Taylor expand these monodromy objects around some suitable values of the spectral parameter. And there's two particular nice values to expand around, and one is z equals infinity. So the Taylor series will look like this, and the coefficients of the Taylor series will then give me conserved charges. Now, the first conserved charge that you will find is something that you actually already know. It turns out to be just the neuter charge related to this global right-acting symmetry, GR. So it's you see here the spatial component of this Marsh-Cartan form L. And this charge is what we call a level 0 charge. The second charge that you find is the one that is written in yellow, so not in red. This is still, well, sorry, I should say the level 0 charge is just this neuter, is just a local charge. The second charge has like this local contribution in the first term, but then it has this non-local contribution here, because I'm taking an integral from -infinity to sigma, and then I'm integrating over sigma again. So this contribution will be non-local. Sometimes it's also called bilocal. It depends really on the reference. And this guy will be called a level 1 charge. Well, strictly speaking, I should still sort of improve. I can improve this charge to be Lie algebra valued. So here, what is in yellow is not really in a Lie algebra, but if I take a commutator and then someone 1/2, then this guy will be Lie algebra valued, and you can check that upon the equations of motions, etc., that this is indeed still conserved. And what is then interesting is that this level 0 charge and this improved level 1 charge will be generating what is known as a classical Yangian algebra under the Poisson brackets of the theory. So the Yangian algebra will be denoted by y r of g. I will not go into much more detail. Let me just say that it's sort of a generalization of a Lie algebra. You can find a very nice exposition of Yangian algebras, either classical or quantum, in these lecture notes by Lubert of 2016. Yeah, and let me also finally mention that for the other charges that are appearing in the Taylor series, there's also a sort of systematic procedure that you can do by induction for the higher charges, such that they are also valued in the Lie algebra. Okay, then another suitable set to value of set to expand around is z is 0 after I performed like a gauge transformation of the monodromy matrix. So I do a gauge transformation by just the fields G, and then I expand around z. What I will find is this Taylor series here. And interestingly, again, here I will find that the first charge will be, again, a neutral charge, but now related to the left acting symmetry. Again, I will call this a level 0 charge. The second charge will again be like this non-local charge that I can improve to be Lie algebra valued. And this will, together with the level 0 charge, this level 1 charge will be generating a left copy of the classical Yangian algebra. So now denoted by an L. Again, this is under the Poisson brackets. So let me point out, because it might be confusing in the beginning, that these sets of charges that we are finding here, these classical Yangian charges, they are not Poisson involutive. But that should not be really a problem, as I told you, because I just need a particular form of the transport matrix. These are just some other sets of charges, and you can think of them as being in some sort of larger hidden symmetry algebra. So this global left and global right acting symmetry, they were quite apparent in the action. These Yangian charges are sort of hidden, and they actually contain also this global G left cross G right. Again, I advise you really to take a look at these lecture notes if you need more information. Finally, let me also point out that this is all true for in the case that the world sheet is an infinite line. In the case that the world sheet is a cylinder for closed strings, things are much more subtle, and it's not really clear whether you can find a classical Yangian algebra. But for some comments on this, you can look at this paper by Hatsuda and Yoshida of 2004.
Sibylle, you have like 10 minutes.
Okay, perfect. Thank you. Okay, so now I discussed a set of certain charges. Let me also, so did I actually? I skipped a few slides. Okay, sorry. I also need to introduce a few, very quickly, these local charges. So here in the case 2, again, you can sort of use this systematic procedure of diagonalizing your monodromy matrix, and then you will find a set of local charges. But interestingly, you also have a different set of charges that you don't find from the monodromy, which are called higher spin local charges. And these are found from observing that the energy momentum tensor for the Principal Chiral Model is sort of classically conformal. So classically, it is traceless. I told you before, at the quantum level, you will generate some RG flow. But using just classically the fact that this is traceless and therefore satisfies this conservation law, allows you to define higher spin local charges by just taking a power of this object. And then the higher spin charges associated to this are given here. And so they are just traces of powers of this Marush-Cartan form. And these are, by the way, in light cone coordinates. So let me just mention here that the Hamiltonian and the momentum of your theory of the Principal Chiral Model are contained in these higher spin local charges and not in these other ones. Okay, so now let's go to the sort of canonical discussion. So whether these monodromy matrices are in involution or not. Remember from previously that if this lax spatial components of the lax satisfy the Sklianian exchange relations or the Maillet bracket, then you're sort of okay. So then you're sure that these charges would be in involution. So what you need to do is like find you know your canonical Poisson brackets of your fields and the canonical momenta. From these you can derive fundamental Poisson brackets in some sense, meaning that they are the fundamental Poisson brackets of the Marush-Cartan form or of this current L. And because this was building this lax connection, you therefore, using these Poisson brackets, you can find the Poisson brackets of the spatial component of the lax to take this form. And you see already here in the Poisson brackets for the currents, this non-ultralocal term appearing, and indeed you also have it in these Poisson brackets. So they will be of Maillet form, and you can indeed check by just identifying the Poisson brackets of the PCM and those of Maillet. that it works. So you can see that you can find an R matrix here, which is sort of a rational form, and you have an S matrix, which is this combination. And let me just point out that this is quite so it's not the standard Young's R matrix, but this has like a function also involved in this in its definition, which is called a twist function, is some function of the spectral parameter. But Sylvain will talk a lot more about this, so we will hear a few more things about this. Let me just mention that this guy also satisfies the classical Yang-Baxter equation. Okay. Okay, I'm sort of good on time, I think. So I can conclude that the Principal Chiral Model, indeed, the equations of motions can be represented by a flat lax connection, which is written down here. And we've seen that the monodromy generates a tower of conserved charges in various ways. And also that these Poisson brackets are indeed of Maillet form, and therefore the traces of this transport matrix will be Poisson involutive. And then we say that the Principal Chiral Model is classically integrable in the strong sense. Okay, but let me just give a few comments on the quantization of the Principal Chiral Model. So having this, I told you that having this non-ultralocal term really complicates the quantization when you want to preserve integrability. There's not a complete understanding of this. Mainly, the road to take is to use symmetries, analyticity, and unitarity to guess your S matrix, and maybe then match it with perturbative results for the S matrix. Now, a sort of progress that has been made a long time ago in case of the Principal Chiral Model is that you can sort of use an alleviation procedure of this theory, where you sort of replace the Principal Chiral Model with another theory that has ultralocal Poisson brackets and therefore is easily quantized. And then if you take, turns out that this theory that Fadeev and Leschetizkin put forward, if you take a non-trivial classical limit of this theory, you would find the PCM arising. So this is sort of back a reversed way of thinking, that you don't want to really quantize the PCM, but you rather want to find it as a non-trivial classical limit of a well-defined quantum theory. Okay, then finally, I will just conclude very quickly with discussing some integrable deformations of sigma models. So there's now a whole zoo of deformations of sigma models, like the PCM, the Westmino-Witten model, or quasi generalizations of them that all preserve integrability, or at least classical integrability. And the main ones that have been studied are the Yang-Baxter deformations, which include TST and beta deformations as special cases. Then there's also lambda deformations and a number of generalizations of all these theories. Now, interestingly, all have in common that this lax connection takes a particular form that I've written down here, where this K plus minus can sort of be thought of as sort of deformed currents. So in the Principal Chiral Model, this was just these ordinary left invariant currents. For the Yang-Baxter and the lambda model, they are sort of deformed. These left invariant currents are sort of deformed. So all of them are classically integrable in the weak sense, but they are also in the strong sense, meaning that the Poisson brackets will indeed take the form of Maillet, and they will involve these twist functions as well. Now the twist functions will be changed, and what happens is sort of these poles of the twist function will get deformed. Now, why are people interested in studying all these integrable deformations? So the main motivation, let's say mainly in the beginning, came from ADS-CFT. So in particular, I told you that ADS5 cross S5 and NS4 super Yang-Mills, they are integrable, and this integrability has been very useful to sort of test this correspondence. But let's say that they are also quite special because, for example, for super Yang-Mills, you have a lot of supersymmetries. So the interesting question is that what happens if I now take an integrable deformation of the sigma model, particularly the one associated ADS5 cross S5, and in particular one that would deform the S5, then what would happen on the side of the CFT? So in the case of TST and beta deformations, this is quite sort of well known. So in this case, the 4 supersymmetries will be reduced to 1 supersymmetry. In all the other integrable deformations, this is still a question mark and a reason why people study this. But more recently, these integrable deformations are also getting a lot of attention from the side of double field theory. So they are starting to have quite a natural understanding in double field theory. And that's also why this workshop is sort of, and many things recently or lately are trying to get these communities of integrability and double field theory together. Right, and that's really everything I wanted to say today. So thank you all for listening. And if you have any questions, then please ask.
So thanks, Sibylle. You're perfectly on time, really. So if anyone has some question, please do ask now, or we can also discuss later, either on Slack or on Gather Time.